So in this video we are going to discuss the question in statistical and thermal physics which appeared in JRF physical science examination in June 2012. The first question is, consider a system of non-interacting particles in d dimension and weighing the dispersion relationship E, that is equal to A k power S, where E is the energy and K is the wave vector and S is an integer and A is a constant. The density of states NE is proportional to. Okay, so I have already discussed this problem in detail in the classroom. So that means the generalized procedure we have already talked about in the classroom. But here there is another additional method which you can follow to quickly determine the density of state dependence on the dimension of the system and the exponent of the wave vector k. Okay, so the result can be generalized from various results which are available for one dimensional, two dimensional and three dimensional system. Okay, so density of states in three dimension, we know that in three dimension density of states, that is Ne, that is proportional to e power 1 by 2. Okay, and this can be written as e power 3 by 2 minus 1. Okay, note that here this relationship, the density of states expression that we have written here, this is valid for the dispersion relationship P E, that is equal to P square by 2m, or that is equal to h cut square k square upon 2m. That's for the non-relativistic particle. So here for the three-dimensional system, S is equal to 2 and D is equal to 3 here. Okay, so here you can make a comparison between D and S here. Okay, now similarly for the two-dimensional system, in two-dimension density of states, that is Ne, it is independent of the energy, that is this is e power 0, and this can be written as e 2 by 2 minus 1. And in one dimension, because these 1D, 2D and 3D cases, they are easy to develop mathematically, and then based upon this conclusion we can generalize the result for the d dimension. So in one dimension density of states, that is Ne, it's proportional to e power minus 1 by 2, e power minus 1 by 2, that is equal to e power 1 by 2 minus 1. Okay, so here if we make a comparison for three different cases, so here D is equal to 3 and S is equal to 2, and in this case D, that is equal to 2 and again S is equal to 2. Okay, and in this case in one dimension system, D, that is equal to 1 and S is equal to 2 again. Okay, so therefore this implies for a D dimensional system with the dispersion relationship of the type E, that is A k power S, the density of states, that is N of E, that is proportional to e power D upon S minus 1. Okay, so therefore B is the correct option here. So let's continue with the next problem. The statement is, the number of ways in which n identical bosons can be distinguished, or can be distributed in two energy level is given by. Okay, so here we are given the number of boson, that is equal to n. Okay, and the number of energy levels are number of energy levels, that is equal to 2. Okay, so the general formula for the distribution of the ozone into various energy level, that is given by W, or which gives the basically the thermodynamic probability or the number of ways, and that is equal to n plus g minus 1 factorial divided by n factorial into g minus 1 factorial. Okay, so here n is equal to n and g is equal to 2. Okay, so for the present situation we are having n plus 2 minus 1 factorial divided by n factorial into 2 minus 1 factorial. So this is equal to n plus 1 into n factorial divided by n factorial into 1 factorial. So this will cancel with this one. So W is equal to n plus 1. So this is our answer. So therefore correct option is A here. Let's take a look at the next problem. It is related to the Bose-Einstein condensation temperature. The statement is Bose condensation occurs in liquid helium-4 which is kept at ambient pressure at 2.17 Kelvin. So we are given T1, that is equal to 2.17 Kelvin. At which temperature will Bose condensation occur if in helium-4 in gaseous state, the density of which is 1000 times smaller than the liquid helium-4. Okay, so first of all we should know the exact expression for the critical temperature and how it's connected with the number density. Okay, so the expression is the critical temperature, that is equal to h square upon 2 pi m kV. kV it's a Boltzmann constant, and then inside the bracket n divided by 2.61 V power 2 by 3, or in other word we can say that the critical temperature it is proportional to the number density via this relationship, it is power 2 by 3. Okay, so with this result we can quickly calculate the new temperature. Okay, so let's call the new temperature is Tc2. Okay, so Tc2 upon Tc1, that is equal to the new density which is 1000 times smaller than the initial density. Let's call n number density, denote the number density by small n, and then in this case it will be n2 upon n1 divided by power 2 by 3. Okay, so n2 is 1000 times smaller than the n1. Okay, so that means this is equal to n1 divided by 1000 upon n1 power 2 by 3. So this is equal to 1 by 10 power 3 and its power 2 by 3. Okay, so n1 and n1 they will cancel with each other, so this exponent will cancel and this one, so this is equal to 1 divided by 100. So that means the new temperature will be Tc2 will be changed to Tc1 divided by 100. So Tc1 is how much? It is 2.17 Kelvin. So that is 2.17 Kelvin divided by 100, and okay, so this is basically equal to 21.7 millikelvin. So therefore B is the correct option here. So let's take a look at the next problem. The statement is the free energy of gas of n particles in a volume V and at a temperature T is given by the expression F, that is equal to nkt ln A naught V into kt power 5 by 2 divided by n. Okay, let's call this as equation 1. where A0 is a constant and kV here I am writing simply K, which is a Boltzmann constant. The internal energy of the gas is, so basically we have to find the expression for the internal energy. We know that the Helmholtz free energy F, it's connected with the internal energy U through relationship F is equal to U minus Ts, or from here I can write U is equal to F plus Ts. Okay, so let me call this as equation 2. But also in thermodynamics we learned that the entropy can be calculated from the known value of the Helmholtz energy, and the expression is S is equal to minus dF upon dt at constant volume. So this is what this result we can derive from the one of the thermodynamic potential that corresponds to Helmholtz free energy, and this is at constant volume. So with this, equation 2 reduces to U is equal to F minus T dF upon dt at constant volume. Let me call this as equation 3. Now what we are going to do is we are going to determine the differential of Helmholtz free energy with temperature by making use of equation 1. Okay, so F can be written as F equation 1, that is, this is equal to N kT ln C T power 5/2. So where C is equal to A naught V K power 5/2 upon N. So we have clubbed all these constant in constant C, all these terms in constant C here. Okay, this is just for the sake of simplification while taking the differential. Okay, so now the differential of Helmholtz free energy with respect to T and keeping volume constant, that is equal to Nk. Now we are differentiating this with respect to T, so T will disappear and ln C T power 5/2 as it is. Okay, now the second term, now nkt as it is, nkt, now differential of the logarithmic term. Okay, so that will give us 1 upon C T power 5/2 and then C T power 5/2 minus 1, and then index we need to multiply by the index, which is 5/2. Okay, now we are going to multiply this result with T, because ultimately here in this relation equation 3 we need T dF by dt. So here we are going to multiply it by T here on the both sides. So T dF by dt at constant volume, that is equal to, so nkt, T will come here, nkt ln C T power 5/2. Okay, plus I am bringing this 5/2 in front here, plus 5/2 and then multiply by nkt, 5/2 nkt, and then 1 upon C T power 5/2 and then C T power 5/2 minus 1 and additional T here, so this will come here as plus 1 here. Okay, so this expression 1 and minus 1 they will cancel, so ultimately we are left with C T power 5/2 here. Okay, so this will cancel with this one, so from here we notice that T dF by dt, that is equal to, now if you just take a look at this expression, this is nkt ln ct power 5/2. Okay, so this is nothing but this is F. Okay, so T dF by dt, that is equal to F and then plus 5/2 nkt. So let me call this as equation 4. Now equation 3 and 4 give us U, that is equal to F minus T dF by dt. So I am going to substitute the value of T dF by dt minus F minus 5/2 n kt. So F and F will cancel with each other, so U, that is equal to minus 5/2 n kt. Okay, so this is the B is the correct option here. Of course, it's not negative sign is not there, but in magnitude this is the exact expression. So therefore B is the correct option here. So let's continue with the next problem. The statement is, a system has two normal modes of vibration with frequencies omega 1, omega 2, that is equal to 2 omega 1. So that is the frequency of two normal modes, that is different basically. Okay, what is the probability? The probability that at temperature T the system has an energy less than 4 h cut omega 1. Okay, so here we are given x is equal to exponential beta h cut omega, and z is the partition function of the system. Okay, so first of all let's try to write the energy spectrum for the given problem. So because we are having two different modes of vibrations, the energy spectrum of the system is given by E n1 n2, and that is equal to n1 plus half h cut omega 1 plus n2 plus half h cut omega 2, where the condition on n1 and n2 are n1 and n2, they can take values from 0, 1, 2, 3 and so on, and the condition is that the total energy of the system E n1 and n2, that should be less than 4 h cut omega. This cannot be even equal to 4 h cut omega. This should be less than 4 h cut omega. Okay, so now basically we have to find out the respective value of n1 and n2 which will satisfy this condition. Okay, so let me call this as equation 1 and this as equation 2, which is a constraint basically. Okay, now we will assign different values to n1 and n2, and then we will try to evaluate the E n1 and n2. Okay, so E 0 0, which is equal to 0 plus half h cut omega 1 plus 0 plus half h cut omega 2, but omega 2 is given to be equal to 2 omega 1, so I will write here 2 omega 1, so h cut multiply by 2 omega 1, and after evaluation this will be equal to 3 by 2 h cut omega 1. Okay, similarly we can do the calculation for the other values of n1 and n2. For instance, E01 will come out to be equal to, you can try it yourself, and this is not very difficult, it's simple, 7 by 2 h cut omega. E02 will come out to be equal to 11 by 2 h cut omega. Okay, and E10 will be equal to 5 by 2 h cut omega. E20 equal 7 by 2 h cut omega, and E30 equals 9 by 2 h cut omega. But we need not to work out the expression for the other higher energies, because as we are noticing here, the energy has started increasing beyond the value of 4 h cut omega. Okay, so now out of all these energy values, we have to only pick those energies which are smaller than 4 h cut omega. Okay, so the ground state energy E00, that is how much? This is 3 by 2 h cut omega, and this is obviously this is smaller than 4 h cut omega, and other energy values are for instance okay, where is yes, 5 by 2 h cut omega. This is also smaller than 4 h cut omega, and this is 7 by 2 h cut omega. This is also smaller than 4 h cut omega, and what about, yes, 7 by 2. So we are having two values for 7 by 2, so that means here we have to take into account the degeneracy also. Is there any other value of 5 by 2 h cut omega? No, it's only the single value. Okay, so 5 by 2, and yes, now so we can with the help of this we can now quickly determine the probability. Okay, so the probability, the relevant probability such that the energy of the system is smaller than 4 h cut omega is given by 1 upon the partition function z, which is given here, it's a z here. Okay, and then the respective values of energy exponential minus this 3 by 2 h cut omega, exponential minus 3 by 2 beta h cut omega, beta h cut omega plus exponential minus 5 by 2, exponential minus 5 by 2 beta h cut omega. Now for 7 by 2 we are having two values, okay, so therefore we will put a degeneracy factor of 2 here, and then exponential minus 7 by 2 beta h cut omega. Okay, in principle this is not omega but omega 1, okay, and then bracket close. So this is equal to, this can be written as 1 upon z x power 3 by 2. What is x? That is e power beta h cut omega. Okay, so here we are taking exponential minus 3 by 2 or the exponential minus 3 beta h cut omega, we are taking it outside, or then, or you can say exponential minus 3 by 2 beta h cut omega if you take outside. So this is equal to x power 3 by 2, and inside the bracket we are left with 1, because here then we will be left with 1, and then here we will be left with exponential minus beta h cut omega, which is nothing but x here. So 1 plus x, and then plus 2 times x square. Okay, here we have made use of the fact that x is equal to exponential minus beta h cut omega. Actually it should be exponential minus beta h cut omega, not exponential beta h cut omega, otherwise we will obtain the wrong result. Okay, so x is equal to exponential minus beta h cut omega. So let's see which option matches with the our result. So it is x power 3 by 2, x power 3 by 2 into 1 plus x plus 2x square, yes, this one, x power 3 by 2 into 1 plus x plus 2x square divided by z. So therefore D is the correct option here. Let's take a look at the next problem. Consider black body radiation which are contained in a cavity whose walls are at temperature T. The radiation is in equilibrium with the walls of the cavity. If the temperature of the wall is increased to 2T, so that means when the temperature is doubled, okay, and the radiation is allowed to come to the equilibrium again at the new temperature, the entropy of the radiation increases by a factor of, okay. So here we actually need to remember the results, that how the entropy, it depends upon the temperature of the cavity under equilibrium condition. Okay, so if you recall what you have learned during the discussion that we had in the classroom while discussing the black body radiation in a cavity, okay, so the energy density, pressure, the Helmholtz free energy, all these quantities, they are proportional to T power 4, and all these expression, these quantity, I'm talking about the photon gas contained in the cavity basically, or we can see the black body radiation in a cavity. Okay, and further the entropy, the heat capacity, and the number density of the photons inside the cavity, all these quantities, they are proportional to T power 3. Okay, or in general for the d-dimensional cavity, it's the dependence is T power d, and here the dependence is T power d plus 1. Okay, so for the present case, because the temperature is changed from T to 2T, okay, so therefore the new entropy of the photon gas will be S2 upon S1, that is equal to 2T upon T and power 3, so that is equal to a factor of 8. So therefore the new entropy will be 8 times the initial entropy. So therefore C is the correct option here.